Now that we've already learned centripetal force and we've started talking about rotational motion, let's double back into centripetal force and talk about it if you know something in terms of angular velocity instead of tangential velocity. You learn centripetal acceleration like this. Tangential velocity squared over the radius is your centripetal acceleration. And that acceleration always points towards the center of a circle, like here with a spacecraft that we're going to do a problem with in a moment. But what if it's easier to know about the angular velocity, how quickly this thing is spinning, what's centripetal acceleration? Well, the equation that governs that, radius times your angular velocity squared. Now that the equation just simply comes from substituting in the equation for tangential velocity. Tangential velocity equals r omega, if you remember that from the relationship in the last video. And so that's going to end up giving you your centripetal acceleration r squared omega squared divided by r, right? And then the square and this r will go away, leaving you centripetal acceleration r omega squared. And so this equation is going to allow you to actually deal with centripetal acceleration whenever you know something about angular velocity, like in this bottom problem. We have a NASA engineer, brand new person, says, hey, I got a great idea. Let's actually assemble a circular spacecraft. This, by the way, has been proposed multiple times in different manners. So let's assemble one of those with a 140-meter diameter in space, and then we're going to start spinning it really fast, and because we're spinning it so fast, we'll create artificial gravity. So the idea then is the people would walk around the outside. So looking at this problem, we have a radius of 70 meters, diameter 140, so radius of 70 meters here, and we're trying to create a centripetal acceleration of 9.81. That way, it would give us artificial gravity, or the same acceleration as gravity, is what would feel like you are getting pushed upwards from the floor. That's the exact same feeling you have here on Earth, is that the floor resists you falling through it with normal force, and so it's like it's pushing up at you, trying to counter out the acceleration of gravity 9.81. So that's the centripetal acceleration we want to cause, and we are looking for the angular velocity we would have to spin this spaceship at. So I created my variable bank. Now I'm going to rewrite my equation, and this is a very simple plug-chug kind of problem. So I come out with the angular velocity of 0.37 radians per second, which really isn't all that bad. Now the tangential velocity is obviously a little bit higher. This times your 70 meters, but that's still not very high, around 25 meters per second, 26 meters per second. So that's not overly bad, especially for outer space. Of course, the real issue with this sort of idea is more of an economical one. You have to launch all that material into outer space, which is incredibly expensive, and you also then have to reassemble everything in outer space. And so that's why maybe this new NASA engineer might propose an old idea that then could get shot down. But in theory, it seems pretty good.